In this chapter, we'll be looking at a brief introduction to organic molecules and organic functional groups. All of this falls under the subdiscipline of organic chemistry. Organic chemistry, formally defined, is the study of compounds that contain the element carbon. Organic chemicals affect virtually every facet of our lives. We have organic molecules or carbon-containing molecules in the clothes we wear, the food we eat, medicine we take. Pretty much any physiological process involves organic compounds because they all contain carbon and other atoms attached to them. Some of these products, we classify them into organic from natural sources or from synthetically produced sources, such as your plastics, etc. Some very simple examples of organic compounds: natural gas, which is methane, that molecule here on the left, or ethanol, which is the alcohol that we see on our alcoholic beverages, your beers and your rums, etc. As you can see, the difference between this methane and the alcohol ethanol is going to be that oxygen-hydrogen group on the right. Other examples of organic compounds include the molecule capsaicin. That is the molecule that is responsible for the spiciness of peppers, and it is also used for topical pain relief. You can see the molecules are a lot of carbon atoms, a lot of hydrogen, and a few others such as oxygen and nitrogen as well. Caffeine is another example of an organic molecule. It is the stimulant found in coffee, tea, soft drinks, beverages, and chocolate, just to name a few. And again, you can see the abundance of carbon atoms across the entire molecule. All organic compounds contain carbon atoms, and most of them contain hydrogen atoms. A few things to note, some general observations. Carbon, because of the way the electrons are arranged or its valence, will always form 4 covalent bonds. Hydrogen, on the other hand, will always form just 1 covalent bond. You can see in this example, again looking at methane, carbon forms 4 bonds with 4 hydrogen atoms, and each hydrogen atom just forms the 1 bond with carbon. These 2 electrons, we represent that bond as a line, just like we did across the semester. Every line represents a 2-electron bond. Carbon, because it can form 4 bonds, it actually has a few combinations that it may take depending on context more than anything else. Carbon can form single, double, or triple bonds with other carbon atoms. You can see here an example of a single bond. This is the molecule ethane. Ethane contains 2 carbon atoms and 6 hydrogen atoms. Now, the bond between the carbon atoms can also be a double bond, in which case you have ethylene, and in which case this carbon atom on the left, for example, will have 1, 2, 3, 4 bonds, and so does the carbon on the right. You can see the number of hydrogen atoms goes down from 6 to 4. Adding another bond between the carbon atoms will make it a triple bond, in which case we have acetylene, right? Acetylene is commonly used in acetylene torches, right, as a fuel source. And you can see the structure is a carbon-carbon triple bond with 2 hydrogens, always making sure that carbon ends up with 4 bonds total and hydrogen has just 1 bond total. Some carbon molecules may form chains, while others may form rings. Here we have an example. This is propane. Propane is the name that we give to the organic molecule that is made up of 3 carbon atoms and hydrogen, nothing more. If it has something other than carbon or hydrogen, it will not be propane. We'll talk about that in a later section when we discuss nomenclature. For now, let's just look at the structure. Because the 3 carbon atoms are bound between them, you need enough hydrogens so that each carbon atom has 4 bonds. You will have a total of 8 hydrogen atoms attached or bonded to the structure. Now the same molecule, 3 carbon system, can form a ring just like this one, in which case we add the word cyclo or cyclopropane to describe this molecule. You can see the number of hydrogen atoms also changes, And we're always looking for that same scenario in which carbon forms 4 bonds and hydrogen forms just the one. Now, other than carbon and hydrogen, organic compounds may definitely contain other types of elements, right? There's no restriction necessary. We call those heteroatoms, as they're different, right? They're different from carbon and hydrogen. Each heteroatom forms a very unique or characteristic number of bonds, and how many bonds it forms will depend on where each of these atoms is located on the periodic table. Some very common examples, right? These are not the only ones that combine with carbon, but they are very common. We have nitrogen, oxygen, and then our halogens, like fluorine, chlorine, bromine, iodine. They have not lone pairs of electrons. They don't really bind, so we just leave them alone. And each atom is surrounded by an octet of electrons. So following that rule of octet, we are able to figure out how many bonds each of these heteroatoms is able to form. Number of bonds plus number of lone pairs has to equal 4, right? Because 4 pairs, 4 times 2, that would be 8. That's the octet rule. Some of the more common binding patterns that you will see in organic compounds are listed right here. Hydrogen, we already discussed, as well as carbon. Hydrogen forming 1 bond, carbon forming 4 bonds. Nitrogen, because it has 5 valence electrons, 2 of them are going to form a lone pair. That leaves you with 3 unpaired electrons and the ability to form 3 bonds. Oxygen forms 2, and then your halogens, which we use the letter X to denote halogens. X can mean fluorine, chlorine, bromine, or iodine. They form just 1 pair, but then they have 3 pairs of non-bonding electrons. These 6 dots that we see right here. The most common multiple bond between carbon and a heteroatom is going to be carbon-oxygen. It's so common that it has its own name. It's called the carbonyl bond, and it tends to form just like the figure on the right. Carbon double bonded with oxygen, and oxygen containing 2 lone pairs of electrons. That doesn't mean that this is the only possible combination between carbon and oxygen. Carbon may definitely, it can form single bonds between oxygen, in which case oxygen has to bind to something else to make sure that it follows the rule where it has two pairs of electrons and 2 lone pairs. Looking at the Vesper theory, valence shell electron pair repulsion, we can predict the shape of a lot of these structures. The Vesper theory is really simple. It tells you that electrons don't like each other. They want to be as far apart from each other as possible. So whenever you have 2 pairs of electrons, they'll be as far away from each other as they can be without breaking the molecule. So for example, when you have 2 groups, just like the one here in this triple bond and then this double bond on the left, the farthest they can be from each other without breaking is going to be a straight line, in which case we have a linear structure, right, separated by 180 degrees. As you keep adding groups, then that geometry changes to whatever provides the least amount of repulsion, or whatever makes these electrons be as far away from each other as possible. This doesn't apply just to bonds, it also applies to lone pairs, and we'll see that in just a little bit. Here we're looking at a double bond, carbon-carbon double bond, and we see that we have 2 hydrogens. And if you look to the structure on the left, you will notice that you have 1, 2, 3 places where you can find electrons. The farthest they can be from each other is separated by 120 degrees. If they try to separate a little bit more, then they actually get closer to the third group. So this is the farthest that they can actually be. We call that a trigonal planar, so a flat triangle, trigonal planar structure. When instead of 3 or 2, you are surrounded by 4 groups, just like the case of methane, carbon hydrogen have a very unique angle of separation, 109.5 degrees, And when you have this structure, we call this a tetrahedral structure. This is super common in organic chemistry, so you will see this configuration, this geometry, fairly often in this chapter. If you're looking to draw a tetrahedron in 3 dimensions, the notation or the system that is used is this one right here. So you have your solid lines for bonds that are in the plane of the paper or the screen. If you're looking to draw a bond that is coming out of the screen towards you, then you do a solid wedge like this one right here. And if you're looking to represent a bond that is going away, right away from you or behind the plane or the screen, then you use a dashed line. That's how you go from the structure on the right to the structure on the left. Every carbon with 4 single bonds is considered to have a tetrahedral geometry. Nitrogen is attached to 3 atoms and has 1 lone pair, making its shape trigonal pyramidal. So it's a triangle, but it's not flat. It's actually in the shape of a pyramid. So trigonal pyramidal. So 3 bonds, you can see forming kind of like that triangle. And then this lone pair sort of pushes everybody else down, getting that that pyramidal shape. Oxygen, on the other hand, is attached to 2 atoms and it has 2 lone pairs, making its shape bent. So it's sort of like a tetrahedron, you can see it right here, but 2 of their corners are going to be lone pairs, and the actual bonding pairs, this one's right here on the bottom part of the structure, that's what the name bent comes from, because it's sort of like bent in that direction. This is just a quick summary of some of the geometries that you'll see. And as you can see, there is a relationship between the shape around a specific atom and the total number of groups, right? We also can look at the relationship between number of atoms and lone pairs and the ultimate shape that you end up getting. Now, when we're talking about organic molecules, there's a couple of ways that we can represent these structures. Which system we use, which way of representing, will depend on context. Am I in a hurry? Do I want to convey a lot of information? Do I want to convey specific information? All of that goes into my drawings. So for example, here we have 4 ways of representing pentane. Pentane is the system that contains 5 carbon atoms, like pentagon 5 pentane, 1 2 3 4 5. So we can do it like this, like a skeletal structure. If we just want to look at the number and type of atoms, if we want to see this actual shape, how they actually bend, then the ball and stick model is actually pretty good at that. We can also do the condensed structure, in which case we just assume that whoever's reading this understands that there is a geometry, but we don't really need to convey that. We just convey the actual positioning of all of the respective atoms. And lastly, we have what we call the skeletal structure. This one is the most condensed, is very commonly used. And basically what it does is that every time you have an end or a peak, you are representing 1 carbon atom. So you will have 1, 2, 3, 4, 5 carbon atoms, and then as many hydrogens as you need to make sure that you have your 4 bonds. So in this case, for example, this carbon here in the corner is forming 1 bond with this other carbon. So it needs 3 hydrogens to form those 4 hydrogen bonds, or those 4 bonds that need to happen in carbon. This carbon atom here on this peak is forming 1, 2 bonds with carbon, so it is missing 2 hydrogens, and so on. And that's basically what a skeletal structure does. In a condensed structure, all of the atoms are drawn in, but the 2 electron bond lines and lone pairs of unheteroatoms are generally omitted. In other words, a lot of these systems assume that you have some background knowledge and that you're able to piece it together. So for example here, if we wanted to, for example, I want to tell you that this carbon atom is attached to all of these, which I'm doing, but here on the structure to the right, I am not telling you that, right? I'm just saying CH3. So I'm assuming that the reader knows that this bonding is happening, right? So it does assume a little bit of prior knowledge, which we already have from basically the rest of the semester. Some bond lines can be drawn in for effect or to show specific bonding. So if you want to show that there is some branching, we call this branching, or that the carbon is just not there, it actually goes somewhere else, or there's something different, then you probably want to draw that specifically in, because you can just assume that the reader is going to know if something is just not in a standard way. Identical groups, you can actually condense them a little bit further. You basically, for example, here you have CH2, CH2 next to each other. You can just draw a parenthesis and say, well, I actually have two CH2 groups. Here, for instance, these two methyl or CH3 groups are bound to this carbon. Okay, then I just use the parenthesis. So you can actually do that so long as you're keeping that integrity of the molecule, right, representing those bonds where they should be, then it is okay. Here we have an example problem. Let's work it out. And it says convert each compound into a condensed structure. So you have here, for example, 1, 2, 3, 4, 5 carbon atoms, all of them with hydrogens. But then if you look at carbon number 2 and carbon number 4, I am counting left to right, then these ones have a CH3, CH3. So I can just write it out in that way. Let's look at our second option here, our second problem. We have 3 carbon atoms, then we have oxygen, carbon, and then chlorine. So one way in which you can actually condense it is the structure here in the middle. 5 carbon atoms, carbon 2 and 4, they have CH3 groups, and then just write everything without the bonds. You can further condense this and say these two CH3s, put them in a parenthesis, and then these two CH3s, you can also put them in a parenthesis. As for the structure with oxygen and chlorine, those atoms need to be not just drawn in, but also drawn in the specific position where they are located, which is what we do here. You can further simplify here, but that's about it. And that's how you condense these structures. Whenever we're doing skeletal structures, we assume there is a carbon atom at the junction of any two lines or at the end of any line, just like we have mentioned before. Assume there are enough hydrogens around each carbon to give it 4 bonds, and if there's anything different from hydrogen or carbon, you have to draw it in. We have an example here. This is cyclohexane, hexane from hexagon 6, in which case we don't have anything other than carbon and hydrogen, so we just draw a hexagon. We assume there is a carbon atom in each one of these and enough hydrogens to complete that 4 bonds. If there is something other than carbon, in this case, for example, cyclopentanol, so pentane 5, cyclo, that means that it is cyclic, and that OL at the end means that you're dealing with an alcohol, something that contains OH. So this is not a carbon or hydrogen, it is an OH, so you actually have to draw it very explicitly wherever it is located. Here you can see another representation of that skeletal structure, and I think the advantage of this is very apparent. Drawing this is out faster than drawing this, and that's usually why this system is so popular. Now let's talk a little bit about functional groups. Functional group is whenever we have an atom or a group of atoms that give your entire organic molecule a very specific chemical and physical properties. Functional groups may contain heteroatoms, multiple bonds, or both. Usually, we represent functional groups in this way. We use the capital R for the carbon backbone, so basically just a generic carbon structure, a line because we want to represent that chemical bond, and then whatever functional group we're dealing with, whether it's an alcohol, a ketone, whatever else, right then. And we'll get into that in just a little bit. The letter R is used to abbreviate the carbon-hydrogen portion of the molecule. Sometimes when it's not relevant, we just want to focus on the functional group, we just place the letter R and move on. Hydrocarbons, those are the simplest functional groups. We've been looking at them for a while. And it's compounds, it refers to compounds that only have carbon and hydrogen. Now, within hydrocarbons, we have a couple of functional groups. We have alkanes, they only have single bonds and nothing more. when you have an alkene, notice that you went from A to E. Now you would have a double bond. And alkynes, you have triple bond. So those are the names for those type of hydrocarbons. Lastly, we have what we call the aromatic hydrocarbons. They contain benzene ring, which is 6-member rings with alternating single and double bonds. As you can see here, this would be a benzene ring. Other groups that contain a different type of atom other than carbon and hydrogen, we have alkyl halides. Those are groups that contain alkyl refers to the carbon hydrogen containing part. Halide refers to halogens. So you're gonna contain one of the halogens. We use an X for a generic, but it can be any of these four. And you have an example here. Alcohols are any organic molecule that contain an OH. You can see it here. This is methanol. We call that OH a hydroxyl group. Ethers are molecules that contain an oxygen atom in between two carbon-hydrogen systems, right, or components. And you see an example here. Notice that these are single bonds. Amines, they refer to nitrogen-containing groups. And thiols, the word thiol, you have a sulfur hydrogen, that's a sulfhydryl group. We have a few examples here of some ethers. We have diethyl ether. Diethyl refers to, this is an ethyl, another ethyl, so diethyl. And then ether because you have oxygen in between those two groups. They can be part of a larger molecule, so you don't need to have just one functional group in a molecule. You can have a bunch of them. It really depends on context. So here we have, for example, the molecule of THC, where you will have an ether. You actually have an alkene, double bond right here. You have an aromatic right here, that ring with alternating, alcohol, OH, and then alkanes, right, single bonds. So all of that coexists in that molecule, so that when pieced in that very specific shape and identity, you have the molecule of THC. Other groups, we call this one carbonyl. I think I mentioned that earlier in the presentation. Carbonyls, when you have carbon oxygen with a double bond between them. Now carbonyls are very versatile. They exist as part of different functional groups. So for example, when you have carboxylic acids and you have esters, just to give you some examples, you will have carbonyl as part of something bigger, basically. So we have here some examples where we have carbonyl, but they are actually a part of a separate functional group. So they can be part of aldehydes. Aldehydes have the R group and then a hydrogen. Ketones, there are two different R groups. They can be the same or they can be different, right? There's no no rule one way or the other. Carboxylic acids, esters, and amides. And you can see the differences between them. When we look at aldehydes, this is actually the simplest one. It's called acetaldehyde. We can do condensed structure, or we can just throw out the molecule. It really depends on how much information we're looking to convey. An aldehyde contains hydrogen atom directly bonded to the carbonyl carbon. The carbonyl carbon is the one with the carbon oxygen. Carboxylic acid contains a hydroxyl group tied to that carbonyl. And you can draw it condensed as well. And again, it depends on whether you want to show the structure or just the molecule itself. Esters contain a oxygen with an R group next to that carbonyl. So we call that an OR group directly bonded to the carbonyl carbon. So here, and this is a type of question that you will see in your homework, identify functional groups in a much larger setting or a complex molecule. So this is Tamiflu, and we want to figure out what the functional groups are in this antiviral drug. So we break down every part that we see, and we try to assign a name to it. If we go back here, for example, this is a good way of just breaking it down. We have a double bond, so that would be an alkene. OR next to a carbonyl, so ester. Nitrogen, that would be an amine. nitrogen next to a carbonyl, that would be an amide, and lastly an ether group, R and then another R. And that's basically what you would need to do when you're identifying functional groups. And I just want to point out that this, just like the example that we saw earlier in the presentation, you don't need to have just one functional group. You can have several functional groups. And in fact, most organic systems that have any type of activity in the body, they tend to be much on the larger side of things. Now let's talk a little bit about properties of organic compounds. Organic compounds, they are composed of covalent bonds. As you can see, we haven't really talked about ions or charges at all. And that makes them unique, right? That means that their properties are going to be a little bit different. Organic compounds exist as discrete molecules with much weaker intermolecular forces. So you don't have those opposite charges creating that attraction, right? So they're just there. That means that their boiling and melting points are going to be much lower than those of ionic compounds. A lot of organic compounds, if they're on the smaller side, they tend to be liquids or gases, while ionic compounds of that same molar mass, they tend to be more solids. I have here a few examples of what organic versus inorganic. So we have here a much larger molecule than sodium chloride. So sodium chloride on one side, 1, 2, 3, 4, that will be butane on the other. Bond then is covalent versus ionic. One is a gas, the other is a solid. And you can look at the various differences in solubility, melting point, boiling point, and flammability. Now, when we look at polarity, polar versus non-polar, we have a wide variety between organic molecules. So whenever you have a carbon-carbon or a carbon-hydrogen bond, those are considered non-polar. Carbon-hydrogen, even though they are different, their electronegativities are so similar that we usually tend to treat it as non-polar. When you have a larger difference in electronegativity, then you have what we call a polar bond. So carbon and nitrogen, carbon oxygen, and carbon with the halogens, they tend to form polar bonds. You can see them here, slight positive charge here, slight negative charge here, and so on. Hydrocarbons tend to be non-polar because they only have carbon and hydrogen. Soon as you add something else other than carbon and hydrogen, then you add polarity to the molecule. So here, for example, they're adding a chlorine to ethane, so now it becomes chloroethane, and it becomes polar. And when it does, then its solubility, boiling point, melting point, all those things change. If the individual polar bonds cancel on the molecule is non-polar. So I think we saw that a few chapters back when we dealt with covalent structures. So here we added two chlorine atoms, but they are both negative here, so they sort of cancel each other. When they do not cancel, then you have a polar molecule, just like you do in this case of methanol. In this sample problem, we're looking at why this molecule is polar. Well, this is a very important sample because when you look at this structure, you're going to be very tempted to draw it just like the structure on the right. However, in reality, molecules don't really take this shape. They take more the shape of the one on the left, in which case the chlorine atoms are not opposite each other, so they don't really cancel each other. That means that they generate a net dipole moment, so it is a polar molecule. That means that knowing that Vesper theory is actually very important, especially at this point when we're trying to figure out polarity in molecules. Now, when we talk about solubility, what we can dissolve where, and this is a very important topic because in medicine, depending on solubility of certain drugs, is how we actually administer it, and that's kind of important. The rule of solubility is like dissolves like. What that means is that polar molecules are going to dissolve in polar solvents. So if I have something polar, I can dissolve it in water, for example. Water is highly polar. If I have something like a hydrocarbon, it's not really polar, then I have to dissolve it in something that is non-polar as well, such as an oil or fat or things of that nature. And just like it says here, polar organic compounds are water soluble only if they are small, contain nitrogen or oxygen that can hydrogen bond with water. So all of that is super important to take into consideration. If you look at these two molecules here, the one on the left, hexane, small, non-polar molecule, that means that I will not be able to dissolve it in water. I have to dissolve it in something else. Ethanol, on the other hand, is small. It is highly polar because of that oxygen atom. That means that I can, in fact, dissolve it in water. When I have something like cholesterol, this molecule right here, very large, there's only one oxygen atom present, not enough to generate a polarity across the entirety of the molecule. So because of that, most of the structure is actually considered non-polar. That means that cholesterol does not dissolve in water. It actually interacts with fatty tissue instead. We have a few examples here, and usually you will see solubility in organic, solubility in water. If a compound is soluble in one, it will not be soluble in the other. So if it's soluble in organic, it will not be soluble in water. Ethanol tends to be a little bit different because it has a non-polar component, but it is considered polar. So you might be able to get it dissolved on both. A lot of the relevance in solubility is in our health, right? In medicine, this is a very important concept, that solubility, because it allows us to dictate how we can actually incorporate certain nutrients into our bodies. So speaking of, if you look at vitamins, they are organic compounds that we need in small amounts for normal cell function. The body cannot synthesize them. You can't just make them, right? You have to obtain them via your diet. Fat-soluble vitamins dissolve in an organic solvent, but not in water. Fat-soluble vitamins have many non-polar carbon-carbon, carbon-hydrogen bonds, and very few, if any, functional groups. On the other hand, water-soluble vitamin dissolves in water because they contain many polar bonds. If you look at vitamin A, for example, or retinol, it's an essential component of the vision, especially in the receptors in the eyes. It also helps to maintain the health of the mucous membranes and the skin. And as you can probably guess, you have a lot of double bonds, a lot of hydrocarbons just all around, and just one OH. So that means that this system is considered non-polar. So it is a fat-soluble vitamin. Vitamin C, on the other hand, you can already tell from the structure, you have a bunch of oxygen, so very polar. So it is actually a water-soluble vitamin, right? It's vitamin C, ascorbic acid as well. And just like that, you can analyze every single vitamin, nutrient, or anything that goes into your body and determine whether it's fat-soluble, that would mean non-polar, or water-soluble, which means that it is highly polar.